Hi everyone, here's our final lesson on rational functions from our Chapter 4 unit. Today we're going to take a look at graphing rational functions. So from the previous class, you'll remember that we looked at how to find vertical and horizontal asymptotes, as well as how to find x and y intercepts of rational functions. Today we're going to take a look at them on a graph. So make sure you have your graphing calculator with you as well, so you can use that as a guide to be able to check your solutions, but the objective for today is to see what we can do by hand, to see what we're able to graph and figure out without a calculator as well. So you'll have learned some of this from the previous year, and what I wanted to look at was how can we use our table of values to be able to give us a guide so that we can estimate sort of what the trends are for our end behavior. Our first example here says y equals 2 over x minus 1, and let's identify some of the characteristics about it before we actually put anything onto a graph. So taking a look at what we learned about our asymptotes, we know here there's nothing that we could factor, so we don't have to worry about a hole. In fact, we could say that is not applicable in this case. But if we want to be able to find out any restrictions we have, we know that x equaling 1 would be one of our restrictions. We could never divide by 0, so that means that we would have a vertical asymptote at x equals 1, and then when we represent that, we could actually do a dotted line here at x equals 1 to show our vertical asymptote. To find our horizontal asymptote, we remember that we divide the leading coefficients by each other. But in order to divide the leading coefficients by each other, we have to make sure that they're of the same degree. So we have 0 x's on top, we have 1 x on the bottom, and if we divide those leading coefficients by each other, we would get a horizontal asymptote at y equals 0. We can answer the x and y intercept, but let's actually hold off on that, and let's also hold off on the domain and range. But given something like this, we now have a little bit of the framework for what our graph's going to look like. And so here's some suggestions that I have. If our vertical asymptote is x equals 1, let's pick a value that's close to the right of x equals 1. So I would pick x equals 2. And then let's pick something else that's going to be a little bit more to the right. So I'm going to suggest let's pick x equals 5. We don't have to say 5, just like we didn't have to say 2. But if you pick 2 values to the right of the vertical asymptote, and then we balance that by picking 2 values to the left of the vertical asymptote, I think that's going to give us a good sense of what our graph is going to look like. Let's try and mirror that on the left side. So if 2 was 1 to the right, let's pick 0, which is going to be 1 to the left, and then let's pick -3 right there. Okay, so then quickly from here, using 2 over x minus 1, we could try to fill in the rest right here. So we substitute in 2, and we're going to get a value of 2 right there. If we sub in 5, then we're going to get let's see what we would have. If we sub in 5 for x right here, we'd have 2 over 4, which would reduce to 1/2. If we put in 0, we would get -2. And if we put in -3, you would get -1/2. Okay, so let's sketch, let's graph these points right here. So we get 2, 2. And we get 5 and 1/2. We get 0, -2. And we get -3, -1/2. Now, based off of what we know about asymptotic behavior, you approach those values, but for extreme, as they get to extreme values, very large numbers and very small numbers, you know that you'll never be able to pass through them. So based off of that, we actually can now make the assumption that our graph is going to look like this. Make sure you put arrows there to indicate that that's going to extend forever, and we'll do the same thing up here too. So it's just an approximation, but we know that I like to use the term, you hug the asymptotes, you get very close to them. And if you're trying to figure out a little bit more in terms of like what's happening at these extremes, I'll just talk about it briefly in this first example, and then I probably won't talk about it much after. But that's all you need in terms of showing your graph. So how do we know that something like this behavior is happening? So if you pick a number like, I don't know, if x was say 10 or something like that, imagine if you put in 10 for x, you would get 2 over 9. But imagine if you pick something like 100 for x, then you would get 2 over 99. But no matter how big a number you put in for x, you're still going to create a very, very small positive y value. And so in other words, it will always just hover above the x-axis, as you can see is what's happening with our function here. Let's do one more thing just to talk about why it extends up vertically and why it goes up so quickly. So imagine where x equals 1, and imagine you pick something like 1.1, something just barely to the right of x equaling 1. Well, if you put 1.1 in for x, you would get 2 over 0.1, and 2 over 0.1 is actually going to be 20. So when you are just a tiny bit to the right of your asymptote, you're going to have a vertical value that's going to be at 20. It's going to be very, very, very upright. And so because of that, that's why our behavior goes up so quickly there. So you don't need any of these points on a regular basis, but hopefully it shows what's happening as you approach these asymptotes. Okay, in terms of intercepts, we can actually look here and you can say, well, you know what, there are no x-intercepts because we have our asymptote right there. So you could say there are none, or you could say not applicable. And then for our y-intercepts, we have a y-intercept at -2 right there. The domain is going to be everything. It's going to go forever to the left, forever to the right, but x can't equal 1. If you say just that, that's okay. If you add on x is all real numbers, that's good as well. And then for the range, we're going to say it goes up and down forever, but it never equals 0. So our range can't equal 0, but it could be anything else. Feel free to check this with your graphing calculator, but for the time being, we're just going to keep it like that, and we'll move forward. Okay, if you're feeling confident with the first example, why don't you pause the video right now and see if you are able to put in those same characteristics with the asymptotes, and then sketch in the rest of our function right here. So there's nothing that we can factor. So once again, we could say that there's no hole. And in terms of an asymptote, I would say once again, x equals 1. It looks like we would have a vertical asymptote right there. And for a horizontal asymptote, well, we have an x to the power of 1 on the top and an x to the power of 1 on the bottom. So we can divide the leading coefficients. And if we divide the leading coefficients by each other, it would equal 2, which means that we would have a horizontal asymptote at y equals 2. Now let's look for a table of values, and let's pick the exact same values here. We have 2 and 5, and let's go 0 and -3. So based off of that, if we want to see what everything becomes, we would get 4. And then if we put in a 5, you get 10 over 4. And 10 over 4 could be reduced to 5 over 2. So you could either say 5 over 2 or 2.5 or something like that. If you put in 0 for x, you would get 0. And if you put in -3, you would get -6 over -4, which would reduce to +3 over 2. Okay, so let's plot these points right here. So we have 2, 4. We have 5 and 2.5. We have 0, 0. And we have -3 and 1.5. You'll notice some similarities in terms of just how rational functions look. So we can now quickly generalize that it's going to look like that with our arrows there. here we go. To answer the intercepts, it passes through the origin. So we actually have an x-intercept at 0, 0, and you have a y-intercept at 0, 0. And the domain would be, well, again, x can't equal 1, but it could be anything else. And the range would be y can't equal 2, but it could be anything else from that. Okay, our third graph is going to be something that we've never seen before, and it's strange because if you look at the denominator right there, you have x squared plus 1. X squared plus 1 is not factorable, and if you're to say, well, what would be the non-permissible values there, you could put in any number that you want for x. There's no restrictions, and so because of that, it can be a different startup. We don't have any vertical asymptotes, so we don't have a vertical asymptote. We don't have a hole because we weren't able to factor anything there. And it becomes troublesome because now we're going to try and figure out, well, how would you ever make your table of values? For a horizontal asymptote, they do both have the same degree 2. So we can divide the 2 and the 1, and we could say, that would say y equals 2 for our horizontal asymptote, which will be right here. And then based off of that, how do we pick some numbers? So this is a tough question to think about what numbers would be good to pick. I would say, if in doubt, start right in the middle. Start with 0. And let's see what happens if we do this. Let's pick one number to the right of it, one number to the left of it, and then go from there. So if we pick positive 2 and negative 2, let's see what would happen. If we put in the point 0 for x, we would get 0, 0. If we put in a 2 for x, we would get 8 over 5, or that's going to be approximately 1 point, well, that will be 1.6. And if we put in negative 2, well, look what happens. When you put in the negative value to these x squareds, and there is no x itself, it's going to be symmetrical. So you would get negative 2 squared, which is 4, times 2, which is 8, over 5. You get the exact same value. And because you only have these x squared values with no x values, you're always going to get the exact same y value, where if you put in a positive x value, it would have a negative x value that would produce that exact same y value. If you want, we could look at another point, but I don't know if this is necessary. But you could say, well, what would happen at 4 and at negative 4? So if you did something like that, you would get 32 over 17. And if you did the negative 4, you know right away, because of our previous example, it's going to be 32 over 17 as well. And so based off of that, we can say we would have 0, 0. We'd have 2 and 1.6. Negative 2 and 1.6, and then the 4 is going to hover just below 2, knowing that 34 over 17 is 2, 32 over 17 is going to be just less than 2, so be right around here or right around here. I hope that's enough for us to kind of get a sense of what it's going to look like. We have a vertical a horizontal asymptote that we know we're not going to be passing through. So we could say something like that. Now, in terms of our intercepts, we pass through the origin, so we're at 0, 0 again. And our domain, we're going forever to the left and we're going forever to the right. So we could say our domain here is going to be all real numbers. We're allowed to put in any number that we want for x. And for our range, we hit a minimum point at 0, and we have a horizontal asymptote at 2. So it's going to be everything between 0 and 2. It can hit 0, so it can equal 0, but it can't hit 2. So it's everything between 0 and 2 right there. Okay, I would say example D is by far the most challenging question that we're going to have here. I wonder when I did it, if I maybe intended it for to be something slightly different, where we could have a typo for something. I'll show you really quickly what I mean by that. If say, for instance, this was a negative sign, it's not a negative sign, but if it was a negative sign, I just want to show what this could potentially look like. On your numerator here, you could say, well, that could factor to be x plus 2, x minus 1. And on your denominator, if you factor out a negative sign, you'd be left with a positive x squared plus x minus 2, which is identical to your numerator. So you'd be left with x plus 2, x minus 1. So what would end up happening in that case is you would be able to reduce, you would have a double hole, and you'd be left with a graph that would just look like y equals -1, with a hole at x equals -2 and x equals 1. And then we'd be done that question already, and we could move on to the last example. But unfortunately, that doesn't say a negative sign in the original question, and I think that instead this is going to cause us a whole lot more pain. So, all right, let's get rid of this, and let's see what we have. So let's see what we could do to rearrange everything. So on the top here, for sure, if you do have a chance to factor something, I think that we should take a look at that. So x plus 2, x minus 1. And then over here, we could factor out a negative sign, and we'd be left with x squared minus x minus 2. And that could become x plus 2, x minus 1 over x minus 2, x plus 1, like that. Okay, so that's going to give us some indications of maybe some things that we can take a look at. There's nothing that can reduce, and it's tempting, but there's nothing there that can reduce. So once again, we don't have a hole. In terms of taking a look at our vertical asymptotes, we would have one here at x equals 2 and at x equals -1. So we have two vertical asymptotes. Okay, in terms of a horizontal asymptote, if you were to divide the leading coefficients by each other, they both are of degree 2. And so the 1x squared divided by the -1x squared would give you a -1 horizontal asymptote. So now we can start to fill in the rest, but filling in the rest in this case is actually going to be a little bit more tedious. So what I would say is, if you're to look at it in terms of different parts, I would divide it into 3 parts. We have our part 1, part 2, part 3. We have our middle part, our left part, and our right part. The middle part is the part that's going to be the most troublesome. So let's actually look to the right and left, and then let's do the middle last. Where x equals 2, let's pick 3 and 5. And then where x equals -1, let's pick -2 and -4. And we can sub in some values right there. And then for this middle region here, well, we have, let's see what we have here. I would say we could pick 0 and 1. And then if that's not going to be enough, then let's also pick 0.5, and let's see what would happen at a half right there. Okay, so to sub in these numbers is going to take a tiny bit of time. So I'm just going to pause the video, and then I'll put up the solutions right here, and we'll go from there. So okay, so magically here's our table of values, and you could take a look at what we have for our points right there. Let's start to put them on, and we'll see some weird things that happen from this graph. So 3 and -2.5. -1, -2, right around here. 5 and -14/9, so that's going to be -1, 1.55 or so. They'll be around there. Okay. -2, 0, and -4, and -5, 9 is right here. Okay, so again, because we've done quite a few graphs that have asymptote behavior, we can see that this is probably going to look something like this right here. And I think we can confirm that this is going to look like that. Okay. The middle region here, with these three values, we have 0, -1, and that should be concerning because we've never had this before, but we've just plotted a point that's on an asymptote. And for the last 2 years, everything that you've heard has said you can't pass through asymptotes, you approach them. To give a more specific definition of an asymptote is you approach asymptotes for extreme values. So as values approach positive infinity and as values approach negative infinity. But for a horizontal asymptote, like we have right here, you're actually allowed to pass through a horizontal asymptote in a non-extreme value through the middle here. So this point 0, -1 is actually allowed because we still have asymptotic behavior for these two areas right here. It's going to go forever to the left and approach -1, and it's going to go forever to the right and approach -1, but we can pass through it in the middle. So definitely something that's a little bit different from what you may have expected. So that point there, that's allowed. And you might want to make a note right here just to say we are allowed to pass through horizontal asymptotes. At non-extreme values. For example, negative infinity or positive infinity. Okay, now given this this big news, what is the rest of our middle going to look like? We have the point 1, 0, and we have the point 1/2 and -5, 9, somewhere like that, and it almost looks like it's trending upwards. And so we would have something that I think is going to look like that, almost like a cubic function. So if you're not sure and you're saying like, I feel like I would have to graph another 10 points to feel comfortable that this is what it's going to look like, then let's use our graphing calculator right now and let's confirm everything. So in your graphing calculator, let's put this in for y1 and y2. I beat you to it and I've put that in already. So if we take a look over here and we go to y1 divided, or sorry, not y1 and y2. Here's our y1. Here's our numerator divided by our denominator. And we graph that, it looks pretty bang on with what we had. Now, as something that you should definitely consider is if you press second graph and you take a look here, you can find a bunch of values that you could do to be able to check some points if you want to. And remember that if you're saying, well, what would something convert to as a fraction, you could always press that fraction, like -1.555555. And if you want to write that as an exact value, you could say second math, enter, and it'll tell you, hey, that equals -14/9. So you can give that a try if you want. But the bottom line is we have this graph that does match up with everything that we were talking about here. So let's answer the remaining characteristics of it. In terms of our x-intercept, it looks like we have two x-intercepts. We have one at -2, 0, and we have another one at 1, 0. And our y-intercept, which we thought would never happen because we have an asymptote right there, we actually do have a y-intercept at 0, -1. And you guys are probably all nervous and going to ask, hey, is that going to be on the test? So that's definitely one of the trickiest things that you've learned in Pre-Calc 12. And for our domain, we're going to go forever to the left, forever to the right. We don't cross through the vertical asymptote, so x doesn't equal negative 1, x doesn't equal 2, sorry, positive 2, but x could be anything else. And for our range, initially you probably would have presumed that y couldn't equal negative 1, but because we do pass through the point 0, negative 1 right there, it actually goes forever up, forever down, and there's no gap right there, so y is all real numbers. I probably should have made that our last example because nothing's going to get harder than that. And I think once we do an example like this, you're going to be like, okay, this one seems a little bit more manageable. Okay, so let's reset. Take a look here. Your first step is factor if you can. So let's see what we could do. I know we haven't had any examples with wholes so far. We get x plus 2, x minus 2 over x minus 2, x plus 1. And the x minus 2's can cancel each other out. And so now that we have something like that, we do have a whole. And we have a whole when x was equal to 2. And then you have to figure out what the y value is going to be right there. So take, to find out the y value of the whole, take the x value and sub it into your reduced form right here. And if we put a 2 into our reduced form right here, we would get 4 over 3. So we know we're going to have a whole at 4 over 3 eventually when we graph that right there. And then in terms of looking at our asymptotes, we do have an asymptote at x equals negative 1. And we have a horizontal asymptote. If you divide the leading coefficients by each other, and we look at this reduced form right here, you would have a horizontal asymptote at 1 divided by 1 at y equals 1. So x equals negative 1, y equals 1. And now we can fill in the rest. So a common question that people ask is, when you're looking to fill in the rest, are you substituting in the values into your original function or into your reduced function? And you want to substitute them into the reduced function. And you want to do that because it's easier, but it's also going to eliminate some of the issues that we have. We still will acknowledge that we have a whole, but you want to look at the part that it's actually going to look like on the graph. So right here, if we have a vertical asymptote at x equals negative 1, let's pick 0 and 2. And then over here, let's pick negative 2 and negative 4. Okay, so if we pick 0, we'd be left with 2 for y. If we put a 2, we would get 4 over 3. Oh, that's actually probably not a good point because that's our whole. Maybe I'll add in one extra point down here. If we pick negative 2, then we would get 0. And if we pick negative 4, we would get negative 2 over negative 3, and that would just equal 2/3. Let's just add in one more point here. If I picked 3 for x, then you would get the point 5 over 4. There we go. Okay, so we have the point 0, 2. At 2, 4 over 3, we're going to say we have a whole, and then we have the point 3 and 5/4, which is just slightly above there. And let's join that. And then to the left of our vertical asymptote, we could say we have the point negative 2, 0, and we have the point negative 4, 2/3. And there we go. Okay, so in terms of our x-intercept, we have an x-intercept at negative 2. In terms of our y-intercept, we have a y-intercept at positive 2. In terms of our domain, x can't equal -1, but x also can't equal 2. You have a hole there, and there's no other x value in which you could have an x value of 2. And then for your range, we're going to go up and down forever, but we know that y can never equal 1. But also, and this is where some of us forget, y can also never equal 4/3. There's no other y value at 4/3 because we had a hole right there. Okay, that's it for today. So maybe ask me in class. I may look to reduce some of these questions right here, but that gives you a sense of how to graph some rational functions. So thanks for joining us.